to listen for and people who could not attend. So as you know, so today it will be a dedicated theoretical talks, and then we'll have also a few talks about more saturation and color glass condensate, also at the end of the meeting. So I guess we can start now. So welcome again, everybody. And we can start with the experimental talk by Tim.
So I'll go ahead and get started then. My name is Tim Rabin. I'm currently at the Michigan State University, and I'm going to be talking about the recent Aderon observation made by D0 and Totem in collaboration with each other. And I'm happy to announce for this talk that the preprint, which many people are probably familiar with, has actually now been accepted by PRL and will be appearing shortly. In case anyone's having trouble with their internet or following along at home without the video, I'll try to either announce the slide titles or slide numbers as I move along so you can follow along. Okay, so moving on to slide 2, we have to do a little bit of theoretical background since this is the first talk of the day, and to get into what we're all going to talk about. So we're talking about high energy particle physics, and over the past century, we've learned a lot, especially some very accurate things about the electromagnetic and weak force interactions. But even up until now, there's far less we know about strong interactions. And a large part of this is because the strong force is strongly coupled and or confining in many kinematic regimes. However, there is much we can still learn. And in one of the kinematic regions where we can still learn things is the elastic scattering in the forward limit or near forward limit. And that's what we're going to be talking about today, elastic scattering of protons and antiprotons. And that's going to lead us to Aderon physics. So why Aderon? Well, this needs a little historical segue. Before the widespread adoption of QCD and perturbative QCD in the 70s as a fundamental theory of the weakly coupled strong interactions, people asked general questions about quantum field theory and how to describe physics, and came up with various models that relied on some just basic assumptions about what we thought physics and quantum field theory should be like. Some of these things go by the names of S-matrix theory, dual resonance models, et cetera, et cetera. And while these were not fundamental descriptions of the fundamental particles of the strong interaction, there are still a lot of accurate, true physical results that come out of this era. So things like optical theorems and Minkowski rules. One of these approaches was known as Rege Theory. And this aims to describe scattering amplitudes by assuming just a few physical assumptions. So things like unitarity, Lorentz invariance, that amplitudes can be parameterized by analytic functions of momenta. And then importantly, Rege theory usually asks what happens in the high energy limit of this theory, where things might be simplified and results can be more concrete. This is the first talk of the day, so I'm going to be a little brief in my description of the theoretical underpinnings, but there are going to be a lot more talks throughout the day about the theoretical description of Aderons. Moving on to slide 4. So with the reasonable assumptions I just mentioned about Rege theory, we find...
Tim, okay, now it's just switched because it took a bit of time to switch to slide 4. So sorry, go ahead.
Oh, no problem. Okay, so with the reasonable assumptions that I just mentioned of Rege theory, as I mentioned, we usually look at a Rege limit, which is when the center of mass energy is very large and it's much large in comparison to any other momentum scale, like the transverse momentum of an exchange process. So in Rege theory, usually one describes scattering amplitudes using some sort of partial wave decomposition. That's what you see on the left-hand side of this equation. And in the Rege limit, we find that the amplitude is proportional to a power law of the center of mass energy, this S to the alpha. That's on the right-hand side. And this is the classic Rege behavior. When people say that they're observing Rege behavior, this is usually what they mean. Now, when talking about Rege physics, usually the dominant contribution to a process is usually the amplitude with the largest real part of the trajectory alpha, so that it has the largest amplitude contribution. And this dominant contribution is historically known as the Pomeron. The Pomeron is a colorless charge parity even object with vacuum quantum numbers. And this is mostly what gets talked about when people talk about Rege physics. But there is also a partner family or trajectory that contributes with odd signature, is charge parity odd and parity odd. And in many cases, this contribution will be subleading to the Pomeron, but this is what's known as an Otteron contribution. Moving on to slide 5. Both Pomeron and Otteron can be described in perturbative QCD. Usually this takes the framework of what's known as the BFKL approach, looking at what happens when gluons regeize in the Rege limit. But regardless, the key takeaway, what I want you to take away is that between Rege theory with its simple physical assumptions and perturbative QCD, we know that there must be some sort of Otteron physics. So next you ask yourself, where do you want to look for Otteron physics? And there's 3 good ideas. There are others, but I'm going to focus on these. The first is to look at the difference between the d sigma dt, the differential cross section between proton-proton, for example, in totem, and proton-antiproton, for example, in d0 region. The second is to look at the rho, what's called the rho parameter, the ratio of the real to imaginary part of the scattering amplitude in the forward limit, and the total cross section. This is a previous result reported by Totem. And finally, the last thing would be to combine results 1 and 2 which are evidence in different T ranges, some, non-zero absolute value of T versus in the forward limit. And that's also what's going to happen in this work. So moving on to slide 6. So where is the Otteron? I was just talking about a lot of physics that was pre-1970s. So you might ask yourself, well, this has been around for a while. Where is it? In most processes, as I mentioned, the Pomeron is the dominant contribution. And Rege limits also often involve non-perturbative physics. So as the exchange momentum is small, oftentimes you don't have a good hard scale that you can do perturbation theory in. And finally, one of the best ways to look for Otteron effects is to compare particle-particle to particle-antiparticle scattering, which usually in terms of detectors is a tricky constraint to satisfy. Putting this all together, it's hard. So how to do phenomenology, regardless of the fact that it's hard, there's still plenty of people who have thought about ways to do Otteron phenomenology. And here's a very, very brief and incomplete list of references. So there are people who have studied it in the perturbative QCD approach and examined that there are various Otteron states or Otteron solutions. There are many general Rege models, which have contributions that are Pomeron-like, Otteron-like, and include other Regean trajectories. And there's even non-perturbative approaches, things that use the stochastic vacuum, all-order Monte Carlo simulations, and stringy and holographic models. Moving on to slide 7. There have even been previous analyses and even experimental searches looking for Otteron physics. So the Pomeron and Otteron model of elastic differential cross-section dip. This is sort of the classic signature that people look for. There was a comparison of PP and PP bar at center of mass energy 53 GeV, which showed about a 3 sigma evidence between PP and PP bar differential cross-sections. But because this is at low energy, there are other mesons or meson trajectories or Regeans that could be contributing. So I've highlighted this experimental evidence on the right. So this is the classic difference that you're looking for. You can see the PP black dots that are triangles sort of dip below and come back up with a bump. And the PP bar open circles are much more flattened. There have been exhaustive model comparisons to ISR data. People have looked at specific models like this Phillips-Barger model and analyzed LHC and Tevatron data sets. People have tried to use model-independent approaches like using a Levy expansion to look at multiple data sets and even found large significance. Again, I mentioned this is just a very brief explanation of some of the models and theoretical background. There'll be plenty more talks today about Adiron, and even one tomorrow by Chung-Yi Tan, also about the Adiron. So moving on to slide 8. So what might you expect as we move away from that low energy into our new high energy regime? Well, as I mentioned, at the low energy, you have meson and region contributions that affect the structure or shape of these differential cross sections. So if these have a big impact, what you might expect is lots of structure or shape changes in the differential cross section. And so on the left is a prediction of what you might see. However, on the right, you see totem data that shows that the differential cross section is actually quite smooth. And the only feature is this classic dip bump that you see, and there's not other features that are noticeable, at least by eye, in the measurements. And this has been verified at totem at 4 different energies and at the Tevatron. All of this seems to be rather smooth structure. Okay, moving on to the experimental setup for this analysis, D0 at the Tevatron. So D0 is an experiment at the Tevatron at Fermilab. This is outside of Chicago in Illinois in the US. D0 collected elastic PP bar data with intact protons and antiprotons using their forward proton detectors, and they collected about 31 inverse nanobarns of data. To do this, it requires unique detectors, so things that I will reference several times called Roman pots, which allow us to detect things close to the beam in the very forward direction. So on to slide 10. Here's an example of the quadrupole magnetic spectrometer that D0 uses. This is, in general, D0 calls their central tracking system and their forward proton detectors. And on the left, you see a graph of what D0 found for PP bar scattering differential cross sections from about 0.2 up to 1.2 GeV in exchanged momentum. Now, during Totem's measurement, they collected about 20 million events, about 10% of which are the elastic measurements we're interested in. On slide 11, I've shown you where Totem is. So Totem is at the LHC at CERN, and it's at interaction point 5 in conjunction with CMS. So it's a separate experiment that is on either side of CMS. And it has also has Roman pots that are planted at about 200 meters away from the ends of the CMS experiment to look for forward protons. Measurements have been taken at 2.76, 7, 8, and 13 TeV. On to slide 12. Totem also uses Roman pots. As I said, they're on either side of interaction point 5. And these Roman pots are part of a movable beam pipe that can get extremely close to the beamline. Just as an example for comparison, during the 2.76 run, an integrated luminosity of 0.4 inverse nanobarns was gathered with more than 7 million elastic event candidates tagged, about the same order of magnitude as D0. Okay, now on to slide 13, where we will start talking about the analysis. So the goal is to compare totem proton-proton data at these 4 center of mass energies to D0 proton-antiproton data at 1.96 TeV. All the totem measurements, in which you can see in the top left graph, which are the colored dots in the top left graph. So all the totem measurements show the same general features. They're smooth, there's a dip, there's a bump. Whereas the D0 data, which you can see in the top right, appears by eye or naively more flattened out, and there's not really a dip bump. So the procedure here is we're going to try to, we don't have measurements at the exact same energies. So we're going to characterize the general features of the totem measurements. And then we're going to use those general features to extrapolate down to a common energy of 1.96 TeV and then compare. On slide 14, before we do this detailed analysis, we can talk about a slightly more elementary comparison. So ever since the ISR data at 53 center of mass energy 53 GeV, people have looked at defining this object called the R ratio, which is the ratio of the bump over the dip in d sigma dt. This has been measured at the ISR, at the Tevatron, at the LHC. And for elastic proton-proton collisions, this ratio appears to decay all the way up to square root of S 100 GeV, but then appears to be flattened out. Now, as I mentioned, the D0 data looks like there's a flattened no dip bump behavior, and they find this R ratio to be about 1 plus or minus 0.21. And assuming this flattened behavior at higher energies and extrapolating down to the D0 energy from totem, you can see a roughly or greater than 3 sigma difference between PP and PP bar. As I mentioned, though, we can do better than this. So moving on to slide 15. I mentioned we want to characterize the totem data in order to extrapolate down to the D0 energy. So the procedure we took is to define 8 characteristic points of the elastic cross sections, highlighted in the top left. Then to determine how these characteristic points change as a function of t and d sigma dt, as a function of square root of s, and then use these, we use data points that were closest to these characteristic points in the case that there was nothing exactly at the characteristic point. And if there was 2 points that were in different t bins or d sigma dt bins that were close to each other, we merged the bins. Characterizing these characteristic points this way gives a distribution as a function of square root of s that can be extrapolated down to D0 energy. The final issue is that totem and D0 have different T bins, and so we need to adjust for this. And after doing this, we can finally compare. So moving on to slide 16. The following analysis was used to examine how T and d sigma dt run as a function of square root of s. We used a times a log plus a constant and a constant times just square root of s times a constant. For simplicity, the same form was used for all 8 characteristic points. This is just an assumption that we found to work, but is not strictly necessary. Now, I want to note that this is not a large extrapolation. This only covers less than an order of magnitude, and at most 4 points, i.e. the data from the 4 totem runs. This is just a simple parameterization that was used. There's not really underlying physics here. Alternate parameterizations were also used, like general power laws, but they lead to all comparable results. Now, fitting all of these characteristic points leads to very good chi-squared per degree of freedom, better than 1 for most fits. And now with all of this work done, we can extrapolate down to D0 energy. So moving on to slide 17. As I mentioned, once you've extrapolated down, the data is not bins, the extrapolated results over to comparable T-bins. So the extrapolated 1.96 data, 1.96 TeV data are then fit with a double exponential. So that's what's written here in blue. Now, this is chosen for fitting purposes only, and we desired it to be as simple as possible. You can kind of think as the first term as a low T diffractive cone and the second term reflecting the asymmetric structure of the dip and bump. Obviously, like most two-term fits, there's going to be a region in which one piece is dominant and then the transition and then the other piece becomes dominant. And you can also use this formulation, if you'd like, to fit the totem, all the other totem data sets, and it leads to good fits and good descriptions. To account for the uncertainties, the Monte Carlo experiments were ran, in which the characteristic points were allowed to vary within their Gaussian uncertainties, and fits without a dip and bump position matching the extrapolated values were rejected, and things with unphysical slopes and intercepts were also discarded. So we got rid of the unphysical fits. Moving on to slide 18. There's one final issue that needs to be handled. There's actually a difference in the overall normalization between D0 and totem. So to account for this, we looked at the optical point, so d sigma dt at t equals 0, where the cross sections are expected to be equal if there are only C-even exchanges. And we require that PP and PP bar optical point cross sections are the same while keeping the slopes of the cross sections unmodified. So we use totem measurements of the total cross section at the 4 center of mass energies. We used a similar extrapolation as before, so a similar 2-parameter fit, and we extrapolated down to 1.96 TeV. And again, other parameterizations were tested and find similarly good fits. Moving on to slide 19, more on the relative normalization. So we use sigma total to adjust for the extrapolated 1.96 TeV totem data to adjust it to be consistent with the D0 measurement. Sigma total is can be written down in terms of the d sigma dt at t equals 0. Now we use the complete extrapolation and assume rho has this value of 0.145, rho being the ratio of the real and imaginary parts of the elastic amplitude, as I mentioned before. And this leads to slightly different d sigma dt at t equals 0, the optical point for totem, 357 and change, versus D0, which was measured at 341. So this leads us to rescale the totem data by 0.945 so that there's agreement at the optical point. Now, the only final thing I want to mention is that this is not some new independent measurement of the differential cross-section at the optical point. This was just a method to find a common, somewhat arbitrary normalization, and this approach we found to be most straightforward and simplest. Okay, so moving on to slide 20. This is the most important plot, I would say. This is the fully adjusted and extrapolated PP bar versus PP differential cross section. So you see everything is in the same bins at the same center of mass energy. And just by eye, you can already see that these two sets of data points don't seem to agree. We can do better than judging this by eye. Moving on to slide 21, we can actually do a chi-squared test to examine the differences between the cross sections. So here is the full chi-squared test used in the paper, where here T and D are the jth order d sigma dt values. There's a covariance matrix included, and then there are nuisance parameters included for both the overall scale and slope. The slopes are constrained to their measured values, and there's the Corneal-Martin theorem, which says that similar slopes should be observed at small t. Then there's a test using the difference of the integrated cross-section in the examined t range, which with its fully correlated uncertainty, and the experimental and extrapolated points with their covariance matrices. Given all these constraints and all the uncertainties, and the constraints on the OP normalization, optical point normalization, and the logarithmic slopes of the elastic cross sections, doing the full chi-squared test with 6 degrees of freedom, remember there's 2 constraints, yields a p-value of 0.0061, corresponding to a 3.4 sigma significance. This was also checked with a Kolmogorov-Smirnov test as a cross-check. Moving on to slide 22. So there was a previous measurement done by Totem to measure rho and sigma total, the total cross-section. This used low T, so T less than about 0.05 GeV measurements or data in a region that was complementary to what I've been talking about here. In this previous result, exhaustive tests of models without a crossing odd or Odderon-like contribution from compete were tested, and they were unable to simultaneously describe both the total cross-section and the rho parameter. Moving on to slide 23. So we have a complementary or independent measurement made by Totem. So these previous sigma, rho, and total cross-section results in a low T region can be combined with this new measurement, by Totem and D0. The previous Totem result showed that the without an Autoron and looking at all the compete models, there were various discrepancies ranging from 3.4 up to 4.6 sigma. We combined these previous measurements with our new measurement using the Stouffer method. And we selected the models from rho and sigma total that were tested previously, selected the models without an Autoron contribution, and showed that without an Autoron contribution, the total combination with the new results leads to a chi-squared of 5.3 up to 5.7 sigma. So this is the main big result from this new collaboration. Where could we go next, or where could you go next if you're thinking about following up on this? We could use a detailed optical point or slope analyses. Future colliders could give us information at higher exchange momentum T, where the Autoron might dominate over the Pomeron. You could do purely perturbative calculations and comparisons in this region, or you can do more model-specific based analyses and see if you can distinguish between various Autoron models that are existent. Okay, moving on to the final slide to wrap up and conclude with everything I've said. We presented a detailed description of PP elastic differential cross sections measured by totem at 4 different center of mass energies. We extrapolated these results down to the 1.96 TeV center of mass energy that totem measured PP bar elastic cross sections without a C-odd colorless gluonic object, without an Autoron-like object. PP and PP bar differential cross sections differ with 3.4 sigma significance. Combining this with previous rho and sigma total measurements, we find 5.3 to 5.7 sigma evidence, which we take as an observation of Autoron physics. And so I think I will stop here.
So thank you very much, Tim, for this nice talk. So are there some questions or comments to Tim? Vlodek, I see the raised hand.
Hi, Christoph. I'm sure you're not surprised to see my hand raised.
Yes.
But before I make my comments, they are not going to be the same that you have heard before, but some will be. First of all, congratulations for approval for the publication. This is, I'm sure, a big milestone for you guys. But I have number of comments, and maybe some of them we can cover in the discussion. First, my major comment is the normalization. We know that the zero data have 14.4 normalization uncertainty. Your method actually predicts the shape of the cross section, which is the sigma dt, at the d0 energy. So I have been puzzled, and I have tried to understand it, and so far I haven't heard a good reason why you need to renormalize the cross section, because you have two values. One is a measured value, the other one is the value that that you extrapolate from existing LHC data, but both are cross sections. So this is the question to Timothy, I guess, at this point.
I think the short explanation I can give is just to say that we expect in the optical point for PP and PP bar data to have similar behavior and be normalized the same. And so after doing the extrapolation down, we simply rescale to find a common normalization between the two of them.
I know what you did, but this extrapolation point will
Sure.
also depend on the luminosity normalization. So that point that you extrapolate to from the zero, for example, which actually is not the right thing to do, and I will tell you in a moment why. That point, when you extrapolate, propagating luminosity uncertainty will also move up and down. So the extrapolated point has an uncertainty also of 14%, and you didn't include it. And let me just one more comment, and then you can respond. Then there is a very well-known phenomenon, and people who are my age or around my age know that there is a slope change at t equal 0.13, which I think still applies to the zero data. And extrapolation is done from the t range of bigger than 0.26. So your reference to this Cornell theorem does not apply because it applies only to small t's, and you're extrapolating from the t's that are above that very well-known experimentally place where the slope changes. Okay, thank you. So maybe
Sure.
you can respond now.
I can have two quick comments, and then we can probably save longer discussions for the very end. But the first I would say is that the extrapolated normalization we find to be within the extrapolated overall normalization of the totem data. We actually do check and find to be within the D0 14.4% uncertainty, as you have mentioned. But then we still rescale to force that there be a total agreement between the two normalizations at the central values. We can discuss in more detail whether or not this is the exact right thing to do, but I think it's a totally reasonable thing to do. The second thing I just wanted to mention is that when I talked about the slopes for the this new measurement, one of the points I was trying to emphasize is that we did not adjust the slopes for this data above 0.2 TeV, as you had mentioned. For the older measurement of totem, that uses measurements below, like I said, about 0.05 TeV. So it should be below this point that you had mentioned where the slope should start to differ. So maybe in future work, we can look more carefully at what the slope change, or is there a slope change in the totem data compared to the D0 data at these higher T values, but that's something that hasn't been done yet.
And if I may add, the point is also, I mean, we took into account, of course, the uncertainty related to the normalization in the chi-squared. I mean, this is taken into account. And the fact to normalize one data set with respect to the other, it's something which is done everywhere. I mean, if you, as I already told you, if you go to the CTEC method of fitting data or MRST or NLO, people doing NNLO or NLO fits, they are doing this all the time. I mean, you adjust, if you want to do some global fits, you adjust the data set between each other within their fully correlated uncertainty. And of course, the luminosity uncertainty is 100% correlated. So all points vary together. And also when we adjust to the sigma dt at t equal to 0, we don't mean that we measure the slope at t equals 0, especially for the D0 data, because D0 data doesn't have very low t measurements. But what we did is to adjust both data set to an arbitrary normalization. We don't say that we measure the slope at t equals 0. So we just adjust both data set between each other. So this was the idea. But again, I mean, maybe we can discuss it longer during the discussion session. But I see Shung Hee has a raised hand also. So Shung Hee, do you want to ask something?
Yes, first of all, thanks, Tim, for a nice talk. But I have a question. Perhaps this also is something which can be deferred to a later discussion. But quickly, in your fit, does that can you imply, or do you commit to a particular view on how the energy dependence of PP and P bar P total cross section asymptotically? Does the difference go to 0, or go to a constant, or increase with energy?
So are you, I just want to be clear about the question. Are you asking like the ratio of the differential cross sections in the asymptotic limit?
No, I'm trying to find out what can you say from your fit. Does it rule out the possibility when you theoretically for the difference of a PP and P bar P total cross section? Does it eventually asymptotically, or within this energy range, is a constant or decreasing with energy or increasing with energy? So this will have a serious implication on the nature of Aldebaran singularity. Is a singularity at j equal to 1, but depends on the nature of the singularity, you contribute to the total cross-section for PP and P bar P differently. So do you have are you rule any particular possibility out or prefer any particular possibility?
So I don't, if I'm understanding your question correctly, I don't think we're ruling any particular possibility in or out because we're only extrapolating the PP data. So we're not saying how the PP bar data will scale as a function of center of mass energy. And I went back, I think this is the relevant plot that you're talking about, that this is the total cross section as a extrapolated as a function of center of mass energy.
Yeah, and Tim, maybe you can show the comparison plot, which was just shown the previous slide, I guess. Because the comparison is really on a small t range. I mean, I'm not going to t equals 0. Yeah, this plot I was thinking. You see, it goes between 0.5 and 1, basically.
I mean, I can say one of the things that attracted us to this analysis was that the range in t, the range in square root of s, the range in d sigma dt is all very small. So we're not saying anything definitively about, you know, any sort of model dependence. We're doing a very simple, straightforward extrapolation over a, you know, a small
we wanted,
order of magnitude.
I mean, to compare the data set where we have measurement only, so in this range. And then, of course, I mean, you can deduce probably some more things, but then it will become model independent. I mean, it will no longer be model independent. Because according to the model, you can deduce maybe something going to lower t or something like that, but then it's not coming directly from the D0 and totem work in that case.
So is it fair to conclude, based on your analysis, that there is an indication of an Aderon-like contribution, but yet you cannot rule in or rule out the nature of Aderon being whether it's a maximum Aderon or minimum Aderon or whatever others you want to characterize?
Yes, that's exactly the type of conclusion we're hoping people take away from this, is that this sort of, the physics that goes into the difference you're seeing in these plots is Aderon-like. And there are various perturbative Aderon states. There are Aderon models, like you were mentioning, maximal and minimal Aderon models, but none of that goes into our comparison. We're just trying to look specifically at a case where we believe that this is dominated purely by Aderon-like physics and show that without an Aderon, we have a very large difference between these two measurements.
Yeah, and then it's the work of the theorists like you, basically, to try to to say the different model. And I know that in the talk of Martinov, I mean, there will be also some comments on the maximal Oderon model and so on. Yeah, so we'll hear about it more today also. Okay, so maybe we need to move on. Other question? I don't see any more raised hands. Thank you, Tim, again. And now we'll move to, let me check with the next speaker. So the next speaker will be, so let's check Motika. So let's check, you should be able to share the slide, I think.
Good afternoon or good morning, everybody. It's a great pleasure to speak to this wonderful audience. So thanks for the invitation. And I was supposed to cover theoretical aspects of the Oderon, but I also feel that it's necessary to supplement it by some phonological information. So please forgive me this little modification, which is, I think, consistent. So I mean, it's very simple outline. So first, a few words of introduction. Actually, the talk by Timothy already gave some information I wanted to give you. So it'll be the overlapping, and then theory, and then I will switch to something which I call more phenomenology. So how to search for the Oderon. Let me start from the landscape. I mean, the general landscape of the Oderon is such that actually we know quite a bit about the theory of the Oderon and various aspects of it. So the information comes mostly from perturbative QCD considerations, which have been developed since more than, I think, almost 40 years now. However, we are hit by uncertainties which come from the fact that we don't know how Oderon couples to, I mean, projectiles we have at hand, so mostly to the proton. And the uncertainties come from the fact that these couplings are non-perturbative and also they are not measured. I mean, the first results have just arrived, but of course they refer to particle observable. And in general, we know little about how the onderon couples to the proton. Actually, we know more about the evolution than the coupling. So we have very theoretical insight into these issues. And experiment, I would say that the first data which can be or considered to be strong evidence for the onderon have just arrived, have just presented. So I would say we have lots of theory, some phenomenology, and little experiment. So clearly, where we should fill the gap is the experimental searches. So I think a lot of effort should go into this particular research field. So experimental search for the onderon. This is something we really need and was very important. So as you already heard, I mean, the onderon question came when people, or I mean, in the 70s, there was an issue whether there's a difference between, let's say, PP and PP bar cross sections. And they are asymptotic theorem, so the general Pomegranate theorem, which says that the ratio of total cross sections of PP bar versus PP scattering, it should go to 1 when the collision energy squared goes to infinity. And now, if the cross sections are constant, let's say with energy or decrease, then of course this means that the gap between these two things should go to 0. However, as we know from Froissart-Martin bound, it's possible for the, is allowed for by unitarity that the total cross-section of PP grows at large S as at the most log squared of S. But this leaves room for, I mean, keeping this ratio equal 1, you still have, or going to 1, you still can have finite difference or even growing with energy between PP bar and PP cross sections. And so this discussion is pretty interesting, fundamental, and I mean, it created a lot of excitation, and I think for good reasons. And I should note here that the asymptotic theorems, which we kind of invoke here, they are always based on unitarity of the S matrix. So the perturbative calculations, like those done within BFKL or Bartosz-Kreciński-Peszowicz framework for the onderon, might apparently violate these theorems just because they are not unitarized. Okay, you heard already about the Rege model, and I would say that Rege theory is something very particular because it has a lot of information from unitarity of the S matrix, which of course has to hold. So the unitarity guidelines here, of course, are very important, but one has to keep in mind that Rege is, in fact, Rege is a model, not a theory. It's a model because this approach assumes that the singularities in the complex angular momentum plane are isolated singularities. This picture actually in QCD does not work, at least in some approximations, because you can have different kinds of singularities like Rege cuts. And then, or maybe multiple dense systems of poles, which are found in particular QCD. So the Rege theory actually is a model, which is a very good model, but is not necessarily the whole truth. So one has to keep it in mind. So it's good approximation, good guidelines, but not exact theorems, which you can take as a fundamental prediction. So as you already heard from Timothy, the amplitudes, which kind of can be derived from the Rege model, assuming the poles, they can be divided into two categories, depending on this signature factor, eta plus minus 1. And the signature factor is related, of course, to C parity of the exchange and also to crossing, so behavior on the crossing symmetry. So, and this is 1 for the Pomeron and minus 1 for the onderon. This has consequences because, as you will see, this makes one of these exchanges more real and the other more imaginary. The trajectories which characterize the energy dependence of the Pomeron exchange are typically described in terms of the alpha of t. T is the momentum transfer, and then we have intercept alpha of 0, which for gluonic exchanges, a leading approximation would be around 1. And then you have the slope, alpha prime, and t. So this linear form trajectories, of course, is not a genuine prediction of any theory, it's rather observation of what happens in hadronic physics, and it has, of course, some basis on grounds if you have stringy picture of QCD interaction at large distances. However, these ratios are not necessarily completely linear; they are approximately linear. Okay, so what I already said, you have the Pomeron, which is the amplitude has this form, and then because of signature factor, the oderon here comes with the I factor, imaginary unit. So if you take the scattering matrix T, then predominantly in this matrix, the Pomeron is imaginary and the oderon is real. But of course, since you have some additional phase factors related to this minus I to power alpha of T minus 1, then you see deviations from this behavior. So Pomeron receives some small real contribution for T matrix, and oderon receives some imaginary correction to its T matrix. And of course, at T equals 0, if you take the real to imaginary part of the original A scattering matrix element, then it will be related to the famous rho parameter, which is rho of 0, T equals 0. But one has to keep in mind this parameter of T may depend on T. It's not a constant function. So for large T, or T which is measured by totem in the deep region, it may be different than it is measured in total cross-section. So I mean, just very because it was already said. So the first evidence that there is a C odd effects in the elastic cross sections was given by ISR, but as already Timothy said, this is in the region where we have about 50 free GeV of square root of S, and there, as you see, the cross sections, maybe will be enhanced in the next plot more. So the cross sections here from PP and PP bar are still splitted because of the mesonic regions. So the sublidic regions which are dominant in the small as a region. So here we are not sure it's oderon or it's like omega exchange or something like that. So one has to be careful with this data. So they cannot be taken in my view as evidence of the oderon yet. Now, which also heard, and we'll hear more about it in next talk, there is some more evidence of the oderon exchange coming from the tension between the rho parameter and total cross section. So the models which are well have a lot of freedom, they find it hard to describe both rho parameter and the total cross section behavior of PP and PP bar if you don't include the oderon. And the work which will be probably presented in the talk by Professor Martynov here does very good job. So this is their result. Probably more on that in the next presentation. And then you see that actually the inclusion of maximal oderon is very, I mean, helps a lot and removes the tension which you had without the oderon. I mean, there's a discussion in the literature or whether the maximal oderon is constitutive entirety, but there is, I think, some window for that. I mean, so there's a paper by Kozamat-Risk in 2019 where they question maximal oderon, but they leave some space for it. So maximal oderon is not easy to realize, but it might be possible. Now I'm moving more to the theoretical part from the phenomenological part, so introductory part. And as you know, the gluon field under the charge conjugation transforms like that. And you now play around with the color algebra of different tensors, you will find that for two gluons, you cannot make a color neutral state, which is C odd. You need at least 3 elementary gluons to make in perturbative QCD colorless state with negative C parity. So, and then you need the tensor, which is fully symmetric in color indices in the adjoint representation to make this object. The other tensor, which occurs in QCD, so antisymmetric tensor, when combined with 3 gluons, will give you the positive parity, so it will enter the Pomeron sector. So 3 gluons not necessarily mean oderon, they may be the Pomeron, but I mean the color part of the wave function tells you where you are. Maybe it's interesting to note that the oderon actually is related to the an object which is the ABC tensor and the generators of the of the algebra in this combination, and this is actually the cubic Casimir operator of SUNC in general. So this is second most universal Casimir operator after a quadratic Casimir operator. So this has deep group theoretical meaning and exists for all SUNC theories from free to infinity. So this is something robust from the group theoretical point of view. Now we are going to description of the Oderon which was built in terms of perturbative QCD. And this is very much rooted in the famous BFKL framework. And this is generalized, in order to describe the Oderon, you have to generalize the BFKL equation to the case where you have more than 2 exchange gluons. So at leading logarithmic order, we have the same, exactly the same ingredients as in BFKL. So the reduced gluons, I mean, the gluons which we exchange in high energy limit are not simple gluons, they are dressed with the other gluons. So we say they regize. Is actually inclusion of virtual corrections into the gluon propagation. And then these gluons interact with each other with so-called BFKL interaction kernel. And when you go to from the BFKL Pomeron to something more complicated, for instance, the Oderon, then you need to include at first approach the pairwise interaction of regize gluons with the same kernel you have in BFKL. And this was noticed and formulated in terms of equations by Johann Bartels, Jan Kwieciński, and Praszałowicz. They are 2 separate papers in 1980, and also another Krakowian, so my former fellow, Tomasz Jaroszewicz, he has a paper on that in the same time. So actually, he then stopped working in high energy QCD, so he's not well known, but he had the same idea in parallel. This is the equation which describes the other evolution, and maybe also more regions if you want. It's called Bartels, Kwieciński, Praszałowicz, or BKP equation, and then it has very nice theoretical properties. For instance, it has a conformal symmetry, or LUC, especially linear to C invariance, and this greatly simplifies the solution of the Oderon problem because this symmetry is very powerful. And this symmetry acts on the transverse position of the regions. So you take transverse plane, and then you put the regions there, and the Hamiltonian, which tells you how the evolution takes place, it has this SL2C symmetry, and this is a very powerful symmetry. So you can simplify your consideration a lot by theoretical arguments of this symmetry. And for instance, it has also more far-going consequences, as we know from works of Lev Lipatov and then Ludwik Fadiev and Yuri Korczemski, who showed that the BKP equation leads to integrable problem. Integrability is a very powerful concept in quantum field theory and quantum mechanics. And the BKP equation actually leads to a system which is related to so-called XXX Heisenberg magnetic chain, where the replace normal spins of Heisenberg. So Heisenberg system is based on normal spins, but here you replace the spins by SL2C spins, which are much more complicated. But the concepts of the XXX Heisenberg chain survive, and you can solve the problem using the, let's say, some methods known from condensed matter physics. So the solutions are given with generalized Bethe ansatz, and a beautiful example of this power of this method was obtaining the intercept of the Oderon spanned by 3 regized gluons in 3 different transverse positions by Romuald Janik and Jacek Wosiek. I mean, they are my colleagues from the same department. And they solved in 1998 the Baxter equation for some operator which described the Oderon, and they found the intercept, which is, the correction here minus from 1 is about a quarter, but then you have alpha S bar. So this is just 0.96, most people would say. So 0.96, very close to 1, but smaller. And then there was a lot of nice work on this direction, kind of theoretical considerations. So the extension of this method was performed for any number of regions. Korczemski, Kotański, Manashow did a lot of work on that. And then recently, Agustin Sabiovera and Grigorios Kakamis, they performed a Monte Carlo analysis of open spin chains in the same approach, and they find integral observation of graph complexity democracy. So they are exploring some technical concepts with this system. It's very interesting. So for theory is the ideal playing ground. Now we are moving to something more practical again. So the Janik-Wosiek solution with decreasing amplitude or cross-section of the energy is not the only one for the Oderon. Actually, there is one solution which is, I think, more, let's say, important for practical considerations, which is Bartel's Lipatov-Vakka solution found in 1999. And this was found by observation of the amplitudes, scattering amplitudes of the Oderon exchange with projectile like gamma star to eta c, where you have only two lines in transverse plane corresponding to two projectile particles. And also they had the same observation concerning the vertex which has Pomeron and two Oderons. They computed the vertex and found the same property. And the property is that the wave function of this Oderon of state always depends on the combination of two transverse momental regions. And when you translate it into transverse position language, it means that you have only two regions. Yes, Martin? Was a question?
I think Martin is not muted yet.
Okay. So when you translate to transverse position language, you find that you have only two sides in transverse plane which correspond to two regions, not three, as you would expect naively. So it's like two regions collapse into one. So we start from three, but two of them are grouped together, and you find a state which looks like Pomeron, superficially, because it has two regized gluons, but they are of different kind, and I will explain of what kind they are. And actually, this is very nice because for two regions, you know everything from the Kel's equation, and you know the solutions. So here the solution comes almost for free, but let's understand what happens. So the gluon regions, the regized gluons which I was talking about, they are compounds. There are pond-like in transverse space, and they resum to orders virtual corrections. And the rapidity evolution is described by so-called gluon Rege trajectory, which is in fact a divergent object, but it's exactly Rege pole, derived from QCD. So gluons are Rege poles in QCD. And in fact, in order to find these trajectories, you resum infinite number of elementary gluons to form one regized gluon. You can think about it as a Wilson line. So if you have fast particles like a Wilson line which goes through your target, and then you couple many gluons to this Wilson line, and then you can separate this coupling into two sectors, so C even and C odd, or maybe actually it's not C even, C odd. Here is about signature, so you can separate into signature positive and negative, and then you find two different regions. So the usual signature corresponding to one of the gluon comes to so-called F region, like F tensor, which you use for the group theory in SU3, but then you also have a D tensor, which already we saw for the Oderon, and this D tensor comes with the opposite signature to normal gluon. So this is something new, and the fact it's unusual comes from the observation that to build this D region, you need at least two elementary gluons. So it's not visible at naive perturbative considerations. You have to have at least two gluons to start evolution of the D region. But once you kind of come to this concept, you will discover that the evolution of the D region is exactly the same as F region, with only different initial condition. So you start from two gluons in this state, the color state, and then you evolve it like F region, so the same trajectory. And also, if you investigate in detail, you find that if you have a system of two regions F and D, so it's 1F, 1D, then interaction with the BFK kernel between these two regions preserves the same structure. So FD after interaction remains FD. So FD is something stable against interaction with BFK kernel. And precisely this is what happens. So this observation of two regions here is one is D and the other is F. So they are different objects but obey the same equation as BFKL. So this is BFKL equation in the sector of odd conformal spins. But then once you know the solution of BFKL equation, you know the solution of BKP equation for BLV Oderon. So it's very convenient. Now, what has been done? more on the other in perturbative QCD. So 2012, it was a very important paper by Johann Barthes, Viktor Fadin, Lev Lipatov, and Gianpaolo Vacca, where they found the NLO corrections to the BKP evolution equation, and the ingredients, most of them were there on place because the trajectory and interactions and so on, they are the same with BKL at NLO, which were known at the time, but there's a new piece, which is a connected 3-to-3 Rege gone scattering amplitude. So this is something new they had to do, and they did. And you evaluated the leading order only, so which is convenient, but then high energy approximation. So this has some complications. Nevertheless, it is done, and we know now order on how it evolves at the NLO. So this is very nice. Now, there were several attempts to see what happens to the Oderon intercept beyond the leading order. And we have no conclusive results, or no theorems, but a few consistent results which hint that actually the perturbative Oderon stays at intercept equal 1, exactly 1, so flat dependence on the energy. And there is a paper of Anastasieva 2009, where she conjectured actually that this happens at the low orders, and she made some strong theoretical arguments, still heuristic, which were all consistent with this conjecture. So this is like theoretical conjecture with some good support, but not really proof. Barthes, Contreras, and Vacca, 2019, and also Vacca and Michael Brown, 2020, they included running coupling effects, and they proved that this doesn't change the BLV intercept stays at 1. There's more hints on that coming from, let's say, string theory, conformality theory correspondence. I will talk about it a little more in a second. And there's a relation between the Oderon and one of the supergravity fields, which actually has trajectory at 1 or slightly below. I will discuss it in a moment. And this is all here, these three considerations, they're all not taking into account the unitarity corrections. So actually, it may happen that the unitarity corrections push the intercept below 1, but this was, I will come back to this later. Okay, this is a dense slide, but to make it short, you know that we can get a lot of insight into QCD, or better say super Yang-Mills theory, but it's related to QCD in some approximations, by taking into account this anti-de Sitter conformality theory correspondence by Maldacena and Witten. And this path was pioneered in our applications by Romualdiani and Robi Peszański in 1999, who actually evaluated super Yang-Mills high energy scattering amplitudes using n equal 4 supersymmetric Sugra interactions between two string wall sheets in the limit when the string coupling is very small, which corresponds to large coupling limit of gauge theory. So at large coupling, we have some results, which are for Sugra or for super Yang-Mills, but they are related probably. So the leading trajectory which they found at large energies is of course the Pomeron. And actually, the Pomeron corresponds to graviton at the let's say string side. When you go to weak coupling a string, you get gravity. So you have graviton as particle, and then Rege's graviton corresponds to the Pomeron. So intercepts goes to 2 at very large coupling. Then there are scalar and dilaton exchanges that don't matter because they have small intercept. And there is one more field, Sugra field, which is antisymmetric field in Lorentz indices, which behaves a little bit like vector particle, and it corresponds to intercept equal 1, modulo logization corrections. And then there's a kind of, this is something which we can match to the Oderon. And this was explored by Yoshihata and collaborators in 2009, and they actually went further because they also modeled the baryons as deep 5 branes wrapped on the S5 of the background, in which we scatter our particles, and they found, let's say, non-perturbative results, which can be related to what we observe in QCD for PP scattering. What was surprising, maybe, is that PP cross sections were found by them to be larger than PPR P cross sections. So this is something which can be maybe tested in experiment at some point. But this total cross sections, not the sigma over dt. So there is a discussion also which Yoshi and colleagues made about these intercepts. So leading one is equal 1, but there is probably decoupling from the matter. And then there is something which is almost 1. And here you have Hooft coupling, which is supposed to be very large. So this is close to 1, but slightly smaller. And in these results, no entirety correction are included. So interaction with graviton may diminish or slow down the growth. And now the same issues can be studied in the language of color dipoles, which is very successful and very intuitive. So it originates from Al Miller's works. And the application to Oderon was made by Yuri Kovczegov, Lech Szymanowski, Samuel Vallon, 2003. And they actually use the same philosophy you have in standard dipole model evolution. So you have your onium scattering on some target, and then you split. So the evolution is obtained by splitting the onium by emission of gluons, larger C limit. And then there is one C odd initial condition for the exchange. And this gives you the other evolution. It turns out to exactly match the Bartosz-Lipatov-Wacka Oderon. And in this framework, it's very easy, relatively easy, to include entirety corrections, because you may, on the top of this Oderon C odd amplitude, you can add more absorptive corrections coming from the Pomerons, and then you obtain evolution equations. And this was done both in the Miller dipole framework and then in the GMWOC framework, where you consider such operator spanned by two Wilson lines. So this is particular about this operator. So it's one is aligned in one direction, the other. So it's like a dipole. But then what's particular is this minus sign, which tells you that when you change, let's say, color with anti-color, you change the sign of this contribution. This is not happening for the Pomeron. Here you would have something else. So this minus sign tells you this Oderon sector. And then you obtain the evolution equations for which are now coupling the Oderon and the Pomeron evolutions. So N is for the Pomeron, O is for the Oderon. And as you see here, so in the dipole framework, for the Pomeron, you have usual decay equation and the positive term coming from two Oderons. So the Oderons support the evolution of the Pomeron, so they make it larger. On the other hand, when you evolve the Oderon, you see that this is linear piece. So this is BLV Oderon, standard one. And then there are absorptive corrections. So the Pomeron amplitude will diminish the Oderon amplitude. So this Pomeron absorbs the Oderon. So this is something which is unfortunate, because it means that the Oderon is suppressed. You know, the Pomeron has strong evolution, and then the Oderon, which is weaker, will get eaten by the Pomeron. Okay, so Pomeron is strong and self-winterizes itself, and the Oderon in dense regime is like diluted or absorbed by the Pomeron. And actually, I made estimates of actually it's 2005, not 15. I made estimates of these effects in some semi-analytical framework, and it turns out that in saturation region, where the Pomeron function, which is phi in this case, is certain representation, behaves like log of saturation scale, the Oderon function is exponentially suppressed with rapidity with quite some strong power. So in saturation region, the Oderon in this coupled evolution equation comes as decreasing with energy as a power of energy. And then in the linear regime, it's different, because in linear regime, the Pomeron grows power-like, and then the Oderon also grows, but much more weak. And this, we can also see from this slide that actually for the Pomeron, there is a scaling. So the function phi depends on the ratio of Q sat over K. In different functional form is not fixed, but this ratio is fixed. And this behavior here, you see that these two functions have different combination of transfer momentum and saturation scale. So here we have no scaling in the Oderon sector. And these results were very nicely, they nicely agree with results of numerical calculation by Yoshihata and collaborators, 2018, when they made full numerical study. Here is in position space. So here is the Pomeron, which kind of moves towards smaller and smaller, let's say, distances. So actually the total cross-section grows here, and the odorron, when rapidity grows, it starts on the black curve and diminishes or decreases as rapidity grows to this, say, orange curve. So this is consistent with this semi-analytical consideration. So the odorron is absorbed by the pomeron. So if we have like a uniform medium in transverse space, then the odorron exchange at large energy should decrease. Of course, this is different when you have like gray disk picture, then you can have some region of constant odorron exchange. Now we are moving slowly towards phenomenology, and then what's most uncertain from theory side in this moment is how the odorron couples to particles. And actually, it's more complicated because there are two odorrons, so at least which we have in game. So one is the BLV odorron, which couples to the dipole, and then the other is the Janik-Wosiek kind of odorron, which has three regions, really three separated regions, and this couples to baryons. BLV can couple to baryons as well, but as a mixture with the Janik-Wosiek. So you have these two two odorrons, and then if you think about the proton, so 3 lines is a proton, then of course proton is highly non-perturbative. It's filled with quarks and gluons and so on, and then the coupling is large. The shape is not well known, so this is something which is extremely hard to be predicted by theory. Maybe lattice could help, but I don't know. So here you are guessing. So here you have to take a guess, and we have no good data to really pin it down. Maybe totem will help, but it remains to be seen. So this is a very uncertain point, and to make it more complicated or harder and also more interesting, maybe proton has a spin, and this spin also may affect the matter distribution of the proton. And I mean, there are attempts to model it as well. For instance, we made one with Johann Bartels in 2007, where we used the Joffe current, so particular coupling of 3 quarks to a spin, kind of spinor corresponding to the proton, and then we make Borel transform to obtain certain wave function of the proton, the light cone. But of course, this is still a model. And along similar lines, there are works from Adrian Dumitru and collaborators who addressed this problem in the color glass condensate framework, and also added one more gluon in paper which came just last month. So this is a work on a kind of understanding the proton wave function on the light cone, which is kind of now, this is a program which is carried out. And now the spin dependence of the odorron is very interesting. It may actually be a tool to measure it in EIC, for instance. And this was very much nicely kind of discussed by Lech Szymanowski and Jan Zhu in 2016. So these concepts are new and I think more and more interesting, but theoretically harder and harder. Okay, so shortly the review of what was done in HERA to find the odorron. So I think we had one of the first papers of this subject, but we followed actually ideas of okay, I was sorry, here we didn't follow anybody. It was our idea to study exclusive production of eta C of proton at HERA. So it's analog of the diffractive JSI photoproduction. And then because of the charge, let's say, conjugation of gamma and eta C, you project the exchange on the odorron. So we had a prediction, and it was about 10 picobarn at HERA. Unfortunately, it was too little, it's too small cross-section to measure, because eta C is hard to measure in experiment. It decays into 2 rows and then into 4 pions, and this is the best kind of decay channel to measure, and it occurs at only 2% of the rate. So this is very hard, particularly to measure. So then it was generalized to other methods like Pi0 and A2 and so on by Engel, Ivanov, Kirchner, Szymanowski. And I will tell you about the measurements in a second. And another proposal, which I think is very attractive and very good and should be explored further, is to measure the odorron in the charge asymmetry in photoproduction. So it was an idea by Stan Brodsky, Carlos Marino, and Johann Ratzmann, 1999, to study forward-backward charge asymmetry in open charge photoproduction at HERA. So if you produce CC bar pair, which is kind of easy mechanism to realize on the proton, let's say, then the amplitude can be mediated either by Pomeron or by Oderon. But then the wave function or the distribution of these quarks is different because it's one case is symmetric with respect to forward-backward direction, and the other case is anti-symmetric. So in the squares of Pomeron exchange or Oderon exchange, in the squares you get symmetric distribution of charm and anti-charm. But there's a contribution which is interference of these two mechanisms because they can interfere via decay products, via the CC bar pair, and then you will find anti-symmetric distribution of charm in the forward-backward direction. And this is what they obtained. And assuming certain coupling of the Oderon to the proton, they found this function. So you see anti-symmetry between charm and anti-charm. So Z factor is how much of photon energy takes to the charm. And their estimate is that the asymmetry would be as big as 15%. This, however, relies very much on this coupling of the Oderon to proton. And nevertheless, this is uncertain, clearly, but nevertheless, this is a nice process. And in particular, it's very good because it's sensitive to the interference, and the Oderon amplitude comes here as the first power node square. So because Oderon is small, then you take linear instead of quadratic, you should gain. So this is a very good reason to study it. And these concepts were further explored in pi plus, pi minus electroproduction by Szymanowski, Tirayev, Hager, and Peer. And then they also searches made at HERA of diffractive pi zero electroproduction. And then prediction of the model, which was based on stochastic vacuum, was 200 nanobars. The results were much smaller. I mean, the upper limit of 40. So you see here, prediction was too optimistic. So no signal. Then there were searches of F2 meson production by, I think, Zeus. And the prediction from theory was 21 nanobars. Zeus measured 3 nanobars. So here you see the little bump corresponding to this F2. But there is a photon contamination which can make the signal. So here it was not conclusive, or clearly the result was much smaller than the model predicted. So of course, this is implication for Oderon searches in ultraperipheral collisions or EIC, because we have to be aware that our current estimates of the coupling of the Oderon to the proton are probably too optimistic. So we have to worry about it. Now another unsuccessful proposal, which was done by first Schefferman, Kiewicz, Lachman, then Bzdak, Szymanowski, Kudel, and myself, was to study exclusive J-psi production in PP collisions and PP bar collisions. So there are two protons going out, and there is J-psi in the middle, nothing else. And then this can be mediated by diffusion of the Pomeron and the Oderon, but also by the photon exchange. Of course, we know that this is something like photoproduction of the J-psi on the proton with, let's say, very mild of soft photon here. So this we predicted, but actually even in prediction level, it was clear that the photon dominates at the LHC. So the photon signal you see is much bigger for the J-psi than the Oderon signal. And indeed, in data, there was no miracle. They are more or less consistent with the photon exchange. So Oderon is hidden or below the photon contribution. Now I'm coming to the end slowly. So I think it's very, very exciting recent developments, relatively recent, so last decade. And this is a spin-dependent Oderon. And this is a very fruitful connection between the QCD Oderon and the Sieverts function in the small x domain. So the Sieverts function is defined as an integrated or TMD gluon distribution in a transversely polarized hadron. So you have spin of the hadron, KT of the gluon, and then X of the gluon or other particle. And this is a piece which tells you about the relative orientation of the spin and KT. So something which makes this difference comes or enters as the Sieverts function. And it has also connection at collinear approximation to Sterman Q functions, which are quark gluon or trigluon. And then in high energy limit, what we are left with is a T-gluon function here, which is related, turns out, to the Oderon amplitude. So the Sieverts function at small x is sensitive or very closely related to the Oderon exchange amplitude in polarized hadron. So this is a very fruitful tool, or very good tool, to search for the Oderon and also to connect it to what we know about Sieverts function. And clearly, the Sieverts function, if you think about it, is related to spatial antisymmetric part of the matter distribution in the proton, because this comes as a difference between KT and spin and KT minus spin. So if you invert the spin here, so it's KT minus contribution with minus KT. So it's something which parameterizes antisymmetric distribution of partons in the proton. And of course, it's related to angular momentum and so on. So the Sieverts function drives single spin asymmetries in the IA scattering, or in scattering of hadrons with one which is transversely polarized. And because the spin direction breaks the asymptotic symmetry of the, for instance, singly inclusive DIS. So you have one more vector in the problem, and then the azimuthal symmetry is broken, so you can measure asymmetries with respect to the spin direction, and this is sensitive at small x to the Oderon. So there are numerous processes suggested to measure it for Sieverts function, and I think, in my understanding, also for the Oderon. So there are plenty of possibilities proposed already, and it seems that for the EIC, one of the most promising observables is the open charm production of a transversely polarized proton target. So electron proton polarized transversely to a prime CC bar X, and then some spin asymmetries, and you should be able to see the Sieverts function and the Oderon. And also, a very recent PRL paper by Renaud Boussary, Yoshitaki Hatta, Lech Szymanowski, Samuel Vallon, they kind of found that you can also measure the Sieverts function, the Oderon, I mean, because this is now closely related by, again, exclusive pion photo production of, or electron production of proton in forward direction. So a lot of activity is now kind of on these issues. So conclusions. In my view, the Oderon is something which in theory is very natural. It has to be there. There is no other option. So the C-odd glue-dominated exchange is present in QCD. But there are two questions: how strong it is, so how strongly it couples to the proton and the maybe projectile, and how strongly it evolves, in what direction. And this is the questions which are, I think at some point we need experimental input. So far, the estimates of the couplings were too optimistic in most cases. And for the evolution, we are not sure. There are no experimental results on the evolution. So we don't know what happens with the Oderon large energies, maybe except of this maximal Oderon fit. This is another input we have in this moment. What's very unfortunate for the Oderon searches is that the absorptive corrections strongly affect the Oderon. So the Pomeron, the C-even brother of the Oderon, kills it basically in high energies, in the black disk limit. So one has to be careful about it and search for the Oderon in the gray disk region. And the lessons from HERA and LHC are that it's rather hard to measure Oderon exclusive processes, although it's most kind of natural, but it's hard just because of the small cross sections. And then I think that the path which can help here is measurements of charge and spin asymmetries, because they often depend only in the first power of the Oderon amplitude of the square, and I think this is a new path, and this should be very seriously considered in the experiment. And the totem result, which we just heard of, is congratulate on that. It seems to be a major step towards better understanding the Oderon, because for the first time we can get something which can fix the theory and give us a good reference. So let me thank you for your attention, and sorry for the dense talk. I wanted to cover as much as possible, so I was superficial probably because of lack of time, but maybe in questions I can deepen some.
So thank you very much. Thank you very much, Leszek, for this very nice pedagogical review for a topic which is not easy. So thank you very much for that. I mean, I see a raised hand by Bodek.
Yes. So can I ask you about this? The C even brother suppressing the C odd brother.
Yes.
How does it? And I will tell you why I'm asking. How does it work for the elastic cross sections? Because one thing that we see in elastic cross sections, that elastic differential cross sections, is that there is a difference in PP and PP bar in this dip region. But then I think we'll hear from Evgeny in the next talk that if you look at the sigma dt at higher root S, which are measured by totem, the difference between PP and PP bar predictions from his model are very small. So is this consistent with what you just said, that this is how suppression works, or it's in some other channels?
Absolutely, yes. I mean, you see, when you think about linearity at high energies, the most intuitive tool I have in mind is the impact parameter density of the scattering amplitude. And then we know from trajectories of the proton scattering amplitudes and from the, let's say, diffractive peak, that we can, in first approximation, say that PP scattering is Gaussian in the transverse plane. Yeah, so distribution of the density distribution of the scattering amplitude of proton is like Gaussian. And now imagine you evolve this amplitude with energy. So the central region of this Gaussian goes up because there's enhancement of the perturbative Oderon before it interiorises, and then it reaches black disk limit. So the picture we have is that the center in impact parameter of PP scattering, so let's say the small distance part, gets to the black disk, and then the Oderon is completely eaten there. So in the center, in the core, you have no Oderon because it's eaten. Now they are tails, yes, large impact parameter tails, and there, if you are too far, then the Oderon, which kind of has to have more matter because there is more kind of, is a more complicated correlation function. So it's like a cubic correlation function. Then for large distances, the Oderon dies out because it's just tiny, because it's very dilute objects which scatter. So you have to be in this gray disk zone where you have some matter density or some scattering matrix density, not too small, not too large. So I would say the Oderon is like the gray ring contribution, which of course is a small part of the impact parameter plane.
Yeah. But let's check. I was wondering, in this region, also the Pomeranz decreased basically faster than the Oderon contribution as a function of energy. So maybe in this region, when you are at higher center of mass energy, we could isolate the Oderon. So maybe this is what we saw in totem, no? Because again, yeah. So maybe this is yeah. Sorry.
Answering the question why it was tiny. Yes, it's tiny because it only has some small support. Yes, so it's, I'm not saying it's completely destroyed. I'm saying it's reduced in the center and weak very far, but so only little contribution from the ring.
Yeah. So I see Shung Hee has a raised hand.
Yes, thanks for this wonderful talk. I do have a question and also a comment. First, maybe perhaps a comment relating to the last question. This idea of the Oderon suppression due to unitarity correction was discussed in the 80s by some of us. And indeed, you would lead to a suppression of the Oderon, but that was purely in the context of an Eichhoff approximation. So indeed, Basra and I have been discussing this whole questions. Suppose the saturation is due to something more involved, like Rege calculus, rather than just simple iconization. Then in that context, the physical picture is lost. Nevertheless, there is potential, perhaps the possibility after unitarization, the Oderon will remain near 1 rather than pushed below 1. So when we concluded the outer will be pushed below 1 was completely due to equalization, which has a simple physical picture that you try to explain. So that question still leaves open whether higher order correction may or may not wipe the outer out. Now, the second question I would like to ask, also perhaps maybe first a comment about your pointing out in ADS-CFT about the decoupling of the J equal to 1 outer round. I think there is a misunderstanding. When we were the first to point out you can associate in ADS-CFT of outer round with the antisymmetric field B mu nu, we fully realize in this approach, leading order calculation, everything is a pole. If it is pole, then it means there's a physical state in the system. Outer rounds being odd, you cannot have 0 mass J equal to 1 particle because this particle doesn't exist. So the residue has to vanish. Nevertheless, in a Rege language, the trajectory is there. So therefore, there is a 0 divided by 0 giving you a finite contribution to the total cross-section, even if there's no state. So the question I would like to ask is, when you say decouple, you don't mean the contribution for this J equal to 1 state wipes out or completely disappear, or it's just, as I was trying to describe, it doesn't exist a massless spin 1 state, which is strong, which is glue ball. Nevertheless, the contribution to the cross-section has to be taken into account.
Yes, I mean, this is actually maybe a question to Yoshi, who is the author of this.
Yeah, I think that's a question for me, right?
Yes.
So,
well, I guess
yeah, so,
for you,
yeah,
because if I may finish the question, when we did our work, we were fully aware of that. So when your paper came out later, I never really quite understood what you mean, because I know there's no such state. So maybe I should have raised this question 10 years ago, or when your paper came out after ours.
Yeah, so we tried seriously to couple this orderon at J equals to 1 to baryon, and we consider this regization. So we have, as you did, analytic continuation in spin, and so our baryon is a D brane, and I'm trying to couple B field to the D brane, and I couldn't do it.
Well, you
should demonstrate that how you in practice how you actually couple this orderon to baryons.
Yes.
Nobody has demonstrated that.
If I may comment, since the supergravity description you can understand low energy in string theory, the low energy state. Indeed, there's no such spin 1 state.
I agree with that, but nevertheless, you said, okay.
May I finish? Okay. So indeed, the state will manifest itself in some sense through axiom. Nevertheless, the trajectory is there. So therefore, when the trajectory passes to 1, the residue has to vanish. So therefore, you do a calculation at that point. There's no such state. But you have to consider as a Rege singularity, then the residue vanish, that there's a T equal to 0 pole, give you a finite contribution.
Yeah, but I'm just to demonstrate that in practical calculation. I couldn't do it, so maybe if you can do it, then please show that.
There anyway. That's my point.
So maybe we should move this to the discussion session. I mean, it's an interesting point to discuss further, and we'll have also some talks. I mean, related also maybe with the glue balls. I mean, so they are also by Dmitry. So maybe the relation between glue balls and Rhodéron is also an interesting topic. I mean, to think about. So maybe we come back to this during the discussion session. So I don't see any more raised hands, so we can move probably to the next talk. So thank you again, Leszek.
Many thanks, many thanks.
So the next talk is the, let me check. It's Evgeny Martinov. As you may know, Evgeny is very sick actually nowadays. He has already breathing problems. So he agreed to prepare his talk. So I will share his talk, and I put also, he wrote down basically all the commands related to his talk. So it was very nice to write down all his talk. So what I can do, I mean, I will present briefly his talk, or what I understood from it, and also helped with what Evgeny wrote down concerning all the commands for each slide, which you have also available on Indico. So of course, I mean, Evgeny prepared everything, so I am only the reader. So all the blame is to me. I mean, if something is not clear, because I don't know, obviously, the details and everything. So please, I apologize in advance for the quality of the talk. So, okay, so let me introduce what Evgeny wanted to say, which is a Frost-Aron and maximum Oderon model approach, so both from theory and phenomenology. So on the outline of the talk, so Evgeny is saying that the report will be devoted to a model developed by Basarad Nicolescu and himself within the framework of an approach based on the hypothesis of the maximality of strong hadronic interaction and complex angular momenta in the S matrix. So it will first present the theoretical base of this approach, the history and the implementation of the model for forward elastic scattering and its generalization to non-zero momentum transfer. He will present briefly the latest results of the totem collaboration that we saw already, I mean, presented by Tim in the first talk, and see how it can be interpreted in the Frost-Aron and maximal Oderon model. And then he will come to the conclusion. So let's start with the introduction of the maximality of strong interaction. So the maximality of the strong interaction at asymptotical energy is the main assumption which he used together with Basarad in the maximal Oderon model. And this was originally formulated by Xu in this reference from 1962. And then it was strengthened by the work of Lukacek and Nicolescu in 1973. So the Frost-Aron is a region dominating at high energy in a crossing even amplitude. Maximal Oderon is a region dominating at high energy in crossing odd amplitude. So the Frost-Aron realized the principle of maximality for the total hadron cross-section. Maximal Oderon realized the idea of maximal growth of the difference of particle-particle and particle-antiparticle cross-section. So this was the idea behind this model. So let me move to the next slide. So now we will move to the main strict result for elastic scattering amplitude. So on slide 6, the rigorous result of the analytic S matrix theory are based on the S matrix postulates. So we'll briefly note those results that are used in the model. First, the Frost-Aron bound, which is the first item, and the Pomerantz-Schuch theorem. The total cross-section cannot grow faster than the square of the logarithm of the energy, while the ratio of the total cross-section for particles and antiparticles tends to unity with increasing energy, as we saw already in the previous slide. 2, according to the Eden and Cornell constraint, the cross-section difference can grow, as it was already mentioned before. 3, Oberson-Kinoshita-Martin theorem is a very important asymptotic result for amplitude at non-zero momentum transfer. It defines, in fact, the form of the main contribution to amplitudes in the case of maximality riding total cross-section. So this is the last part of this slide. So let me move now to the next slide, slide 7. So for the first point is that the dispersion relation determines the interrelation between imaginary and real part of the Frost-Aron and maximal Oderon contribution. Fifth point, the Frost-Aron is mainly imaginary contribution, while the maximal Oderon is mainly real contribution to amplitudes, at least at low T. And it is also confirmed using the experimental data. Let me move to the next slide. So we'll now discuss briefly the history of the Oderon and the maximal Oderon. So there is on slide 9 quite a few original papers that were published, so kind of historical aspects. of the hypothesis of maximal strong interactions and maximal Oderon. So in 1973, so probably the first time that the Oderon has been suggested was the paper of Joyson, Leader, Nicolescu, Lopez in 1975, that is shown here at the second paper. Further, there were a number of works, some of them are quoted here, so which were published in which the properties of models with Froissart and maximal Oderon and various versions of models were compared with experimental data. So on slide 10, there is some more papers that are discussed. So in fact, there are papers that came, I mean, also the totem result that you know that were already discussed by the team in the previous talk. And also more recently, the paper by Martinov, Nicolescu, and Martinov, Tersoninov, which are quoted, these two papers, which are here. So basically, so this was a generalization of the FMO model to non-zero momentum transfer. So what we will discuss now is basically the main aspect of these two papers. So let me move to the next slide, which is discussing, we'll go briefly because it was presented by Tim, the totem data on elastic PP and PP bar cross-section. So illustrated on this slide, which is a short summary on the first result from totem, again, comparing between the raw measurement and the sigma tot measurement. You have these measurements which are compared with the series of complete measurement in the bottom left plot. So this is basically to show that none of the model were able to describe the data at certain TeV from totem, which is related to the raw measurement, and also the total cross-section. So there was some tension in the data that were already discussed. So on slide 13, let me move to the next slide. So what we mentioned is that the complete analysis and many descriptions that exist of PP and PP bar forward data before LHC era didn't discuss the Oderon contribution. When the paper by Martinov and Nicolescu was in archive, they asked themselves why the Oderon was neglected in most part of the model, why the various estimation allowed to do that. So what they did, they plotted the partial contribution to the imaginary and real part of the amplitude at t equals 0 that they obtained in the maximal Oderon model for forward scattering. And they found that only at high energy, so basically at LHC energy, the solid blue line on the figure that you see as a function of square root of s on the plot which is shown here becomes visible. So only at high energy, it is expected to be able to be seen. And that's why it was important to check if we see it at the highest LHC energy. So on the next slide, so on slide 14, we will discuss now the amplitudes in the FMO model, so the maximal Oderon model. And basically, we'll start by discussing the Froissart and the maximal Oderon part at t equal to 0. So the standard assumption about red dipole and its trajectories is that they are the single poles in the complex J plane. Trajectories are approximately linear in T. That is confirmed in spectroscopy of the hadronic resonances. Froissart-Martin band requires that the intercept of all trajectories with vacuum quantum numbers could not exceed 1, as everybody knows. So how is it possible to describe the rising total cross-section with such restriction, and which kind of regions is suitable for that? As it is shown in the slide of Pomerance singularity with linear trajectory will violate unitarity, as it is mentioned here. So let's write a general enough form of region contribution with two parameters m and n, that is shown in the bottom formula, and taking into account that amplitude at t equals 0 as not any t singularity. If the total cross-section and integrated elastic cross-section are rising proportionally each to other, we obtain m equal 2 and n is equals 3/2. This form is used in the maximal Oderon model, imaginary and real, for the main terms of Froissart and maximal Oderon correspondingly. So I will come to slide 16 now. So basically the PP and the P bar P amplitudes are written as a contribution of the Froissart and Oderon maximal and effective crossing even and crossing on region with intercept, which is about 1/2 or even less. So the main terms in the Froissart and maximal Oderon correspond to J with omega equal J equal 1, J minus 1, sorry, the form which was given in the previous slide. Other terms in F and OM are corrections in log S. So the standard Pomeron and Oderon with intercept equal to 1 are not considered at t equals 0 because their contributions to A, the amplitudes for PP and the amplitude for PP bar are constant. They are absorbed in the term that are written here, which is the H3 and O3, which are basically as well constant. So these terms would be distinguished at t when t is different from 0. And the amplitudes that are written here have about 10 free parameters. So let me come to the next slide. So what is on this slide? So there are 3 parameters of the model were found by the standard minimization of the chi-squared as usual, I mean fitted to the data. And we show the results which are compared on these 2 figures. From the fit of the data in the energy region from 5 GeV up to 13 TeV, so many data that are available, they obtain a chi-squared per degree of freedom, which is about 1.67. The best prediction of the complete without Oderon is shown for the dashed line, just for comparison, compared to the maximal Oderon model, which is basically, you see on the right, this is the full red line as an example. And on the left plot, you have it also at the full red line. Let me move now to the next slides. So the second part we are going to discuss is how we can extend this maximal Oderon model at t is equal to 0. So what is done in order to verify the stability of the considered maximal Oderon model? So they performed a fit procedure with a more general version of the model. So for this, they considered the original Eden and Corny bounds for PP and PP bar cross section, their difference with the 3 parameters that are introduced, which are beta F and beta O. The intercept of the standard Pomeron and Oderon were 3 as well, but less than 1. After the fit, they will find the following results that are discussed in the next slide. So now we will discuss on all the results which are shown here. The main results are described here. So beta F and beta maximal Oderon, if they are free, come back to the saturation value. So beta F is equal to beta MO is equal to 2. Pomeron intercept comes back to 1 from any input value which is less than 1. More detail concerning the standard Oderon are given in the paper if you want to see more details in this physics letters paper. And if we put 1 to 0, no maximal Oderon, the description of the data is bad, and the chi-squared is going from 1.07 to about 1.18. So this confirms that the principle of maximality of strong interaction works. The Froissart and maximal Oderon are necessary for successful description of the forward LHC data. So now let me move to the slide 21. So the part will be discussing the Froissart and the maximal Oderon at t equals 0, different from 0 now. So let's come back for the moment to the simple reasoning and the assumption in order to choose the generalization of the maximal Oderon model for t equals 0. So we take into account that in the transformation from the phi as a function of omega and t to a to the amplitude with the plus or minus components at high energy, the main contribution to the integral comes from the region around the singularity of this, basically this phi observable. So we suppose that in agreement with the structure of this singularity at 0 in the denominator, the numerator of phi minus, which is beta minus as a function of omega and t, is a function of kappa of t. That is basically written on this formula. Then the numerator can be expanded in powers of kappa as small values of kappa. So on next slide, so on this slide, so it's just a reminder of the definition of the PP bar and the PP amplitude, and for their crossing even and crossing on terms, you have basically the first term, which is the amplitude of a PP scattering, and here for the PP bar scattering. On the next slide, so we show the following the above arguments. They used in the maximal Oderon model for Froissart and maximal Oderon the parametrization that are shown in this slide. The explicit form for the vertex function is chosen after comparison of the results obtained in the fit with the exponential in T vertices, and those written also in this slide. So on the next slide, we show that the Froissart and the maximal Oderon are important in the whole kinematical region. However, they start to dominate in the TeV region. So basically where Totem did the measurement. The standard Pomeron and Oderon are important in GeV region, and the cusps tune the d sigma dt region around the dip and the bump structure, and in the second diffractive cones. A role of R terms is not clear enough, however. Nevertheless, they help to obtain a better description of the considered data, despite that they consider the region where T over S is small. Secondary, regions at T non-equal 0 are important at Fermilab at ISR energy, but they are becoming negligible, starting from an energy above 100 GeV. So it means that at Tevatron energy, or also at the LHC energy, where we have this comparison between PP and PP bar interactions, this becomes negligible. So you have here in this plot, I mean, this is a comparison on d sigma dt as a function of t for the different data that were taken for different energies. So it's, the energy is written in the figure, and they are compared with the maximal Oderon model. On the next slide, you see now the same for the energy. So we compare both for PP and PP bar. I should mention about the quality of the fit. The result of the fit is a chi-squared per degree of freedom, which equals approximately 1.6. So there are still some defects in this description, and they are probably not crucial, and they are working now in order to fix the problems, or I mean to improve the chi-squared per degree of freedom for all the values of square root of S. So this is also the slide for now the different, again, comparison between the FMO model and the different data. And this is again now for the cross-section for this, again, the data that are coming at a higher square root of S, or a domain between a few GeV up going to TeV range for the total cross-section. And on the next slide, on the slide 30, so basically now, so this brings to the conclusion that has been written by Evgeny. So when we say discovery of the Oderon, we do not mean global resonance with quantum number of Oderon. Generally, global resonance either of Pomeron or Oderon kind cannot be detected in PP elastic scattering. They must be searched in inelastic processes. In elastic PV processes, Pomeron or Froissart and Oderon only manifest as a region. From the beginning, we consider Froissart and maximal Oderon as more complicated singularities in the complex angular momentum plane than single Rege poles. So the first point is that the main properties that is written in the second bullet here of the Froissart and maximal Oderon model are determined by the hypothesis of maximality of strong interaction and follow from the rigorous theorems of the analytic S-matrix theory and theory of the complex Rege singularities. From the beginning, Froissart and maximal Oderon are considered as more complicated singularities in the complex angular momentum plane than single Rege pole. Second bullet, for the totem, I mean the values of PP, total cross-section, and the ratio rho measured by totem as 13 TeV can be described and treated as Oderon effects only if the maximal Oderon contribution to amplitude exists, i.e. a parameter 0.1 in the maximal Oderon contribution is not 0 for the parameter O_1, if you remember this parameter. And third point, until now, the FMO model is the only physical model, not just parameterization, which does not violate the main unitarity bounds for physical observable, and it can describe the data in a wide kinematical region and explain also the latest totem experimental result at highest LHC energy, and also the comparison basically with D0, even if there is some studies that are still being done by Evgeny and Basarab also to compare with the latest publication between D0 and totem. So, so Evgeny, thank you very much for your attention. And of course, he apologized that because of his health condition, unfortunately, cannot give his talk. So of course, I could not give such a good talk as he is. I'm not a specialist, obviously, by far of this model, but I tried as good as I could, to describe the talk that Evgeny nicely prepared and also wrote down all the comments of the site. So they are all available on Indico. And if there are some urgent questions, people could ask it. I know Evgeny is connected and can hear the questions, but you can also contact him also directly and ask him questions and comments to this email. And it would be nice, if we follow also this discussion, so you could put me also in copy if you agree, and we could follow up also on any kind of discussion. So let me stop sharing for now and ask if there are some questions again, or clarifications or whatever that people might ask, to Evgeny. I'm not sure if Evgeny can answer, again, due to his very unfortunate health condition, unfortunately, nowadays. And I think on behalf of all of us, we will wish him a very good recovery and hope that we will be back with us, again, presenting his talk to us himself, as it was done before, and we wish him a very, very good recovery very soon. So Vlodek, yes, you have maybe some question. Again, I'm not sure if Evgeny will be able to.
I think I have a comment, but maybe mostly to the D0 totem. But I would like to join you thanking Evgeny for preparing this presentation. It is very educational and pedagogical, so I'm sure we all I will benefit from this, even though I have had many discussions with him anyway. So thank you, Evgeny, for putting all the work to explain to us this whole topic. But at this point, the only suggestion, Christoph, is maybe it would be good to show some of the Evgeny's predictions on your plots, right? Because this is not only for rho, but for the sigma dt.
And I know definitely Basarab and Evgeny are working on it. I got a private preliminary version, but I don't want to show it before they finalize everything of it.
Okay.
But it's only a private because Evgeny is working heavily on it. Despite his health condition, but he's working very heavily on it, right? So maybe Evgeny say something. I don't know if he can express on Evgeny. If you cannot talk, you can always type it, and then we can read it on the chat.
So, okay, I thought it was a public thing because
no, I don't think
it's all private. Okay, all right, thank you.
All right. So Evgeny, do you want? If you cannot talk, you can type something. We cannot hear you if you want to, or if you want to say something or type. You are muted, Evgeny.
Okay. Are you hear me?
Yes.
I'd like to thank you, Christoph, for help in presentation of our work. I could not say answer for questions. I will try to write answer and send who interested to ask me something. Thank you.
So thank you.
Thank you.
Thank you, Evgeny. And definitely, again, we wish you, a nice recovery very soon. Yeah. Thank you. And again, so the best way to contact Evgeny is by email, and then put me also in copy, as we say. Shunki, you want to say something?
Well, let me first say that I wish, like everybody else, wishing you good health, and it's nice to hear from you, your voice. It's been many, many years when we last met, and hope you will recover from your health situation quickly, and maybe we can meet at the next meeting in person. Now, I have a question. Perhaps will be Christopher. Christopher, you can answer. In your analysis, can you say something about this? Well, I no longer see the slides. This is either A1 or N1 is non-zero.
Let me share them again. Sorry.
What they claim that is the signature of maximal Adderall in the last page in the summary.
Yeah, so I mean, for now, I must say that from the analysis that we did between totem and D0, we didn't compare to any model, as also Vlodek was saying. So this will be also the next step, basically, to discuss both with Basarab and Evgeny, to have also some comparison with the maximal Oderon model or any model that people may propose. I mean, this is definitely the next step, to see how we can constrain the different Oderon model using this data. So this will be, of course, model dependent. And Chungri, you are very much welcome also to if you have some prediction or something, you are very much welcome. So to discuss with us. So anybody who would like to use our data and compare with the data is very much welcome to do so. I mean, this is definitely what I want to say.
So in particular, are you able to extract this parameter O sub 1 in this analysis, in your analysis?
I don't know, I must say, because we didn't start. I mean, maybe I don't know, maybe Evgeny can answer either by email or on the chat, but I must say on the D0 totem side, I don't know, because we didn't do this comparison.
Okay, thank you.
I think if I may say something, the way I understand those fits is there's one slide before or so where it is stated that you get a better chi-square with O1 being non-zero.
Yes, I forgot how it was.
And then that's the only thing we know. And also I want to make a comment that it seems to me that the main effect of the Oderon is not in the total cross section, that maybe addresses Chung's comment from earlier, is not in total cross sections, it's in the raw. If you look at the curves that were shown.
Yeah. The raw and the total cross section together that were shown before. Go back to this. Yeah, here it is.
Yeah, no, it's the next slide where you have total cross sections with the fit. Okay, it doesn't matter. You can see that the main effect is in the raw, basically.
Yeah,
and that would depend very much your extrapolation to t equal to 0 on that.
I'd like to add, sorry for my speaking, I'd like to add only the fact that if we put O1 equals 0, we totally destroy description of sigma total and rho at the LHC energies. I did not show the figure, but figure is terrible without maximal Oderon.
And from the totem measurement, so this is coming to the very low T measurement that were done at 13 TeV. So that's why it's going to 10 to minus 4, I mean, in T. So very, very low T measurement for this rho and the sigma tot measurement. Whereas the D0 totem comparison, I mean, as it was shown in the first talk, come to a region of T which is completely different. I mean, it's the 0.1, let's say 2.5 GeV squared or 0.6, I mean, the order of magnitude. So it's completely different domain in T. So that's why they're independent data. So rho sigma tot on one side, which is 10 to minus 4, 10 to minus 3 GeV squared in T, whereas the D0 totem is something, again, like 0.5, I mean, 0.4 in this region of T. So very completely different domain. Okay, so if there is no more questions, so I think we should thank again Evgeny, I mean, for preparing this talk and writing everything about the talk that you can go through again. It's put in the Indico. I mean, despite his health. So thank you very much, Evgeny, for doing this on behalf of all of us. And again, wish you a nice recovery. So I think now we have the coffee break, if I remember well. Yes.